So that I'm here from QUT, Queensland University of Technology, down in Australia under the supervision of Dr. Frederick Mayer. And my work mostly looks on 3D inference from monocular vision, or as I like to say, I solve hard problems badly. Right? There's lots of ambiguities in there, lots of things you can't do perfectly just with geometry. But my main philosophy is if you're not using computer graphics techniques in computer vision, then you're trying to learn too much. Right? As I said, there are ambiguities. I do feel in computer vision you do need to learn some things, right? But that doesn't mean you have to learn everything. Today we're talking about a couple of papers that explain most of the theory in terms of human pose estimation because that's a bit easier to get the head around. It's a bit of a toy problem, as we'll see. At least the part that I focus on is a bit of a toy problem. And towards the end, we'll look at some single view reconstruction stuff as well. I would prefer you guys, if you've got questions, to stick up your hands and ask them throughout rather than waiting until the very end. I'm happy to address them, and I promise if I'm just about to get to the answer, then I'll just tell you to wait for a slide or two. Okay, so problem with human pose estimation. I'm hoping we all are familiar. Is anyone not familiar with human pose estimation? We'll roughly, the idea is given an image, right, we're going to try and locate where someone's joints are in either 2 dimensions or 3 dimensions. So we'd be given this image without the green overlay, and the challenge would be to find the green overlay. Right? This comes in a couple of variations. Right? Number one is the 2D version. Right? So given an image, try and infer the joints in 2-dimensional space. In terms of data sets, there are a fair few out there. They're normally human annotated. Right? So we set up a whole bunch of images, and generally Amazon Mechanical Turk or some other service will get people who will work for very little money to do fairly dull tasks of annotating this data. Per example, it's kind of expensive. Depending on your definition of expensive, it might take sort of 20 cents per frame. Right? But normally we have very varied images. So not many cases of the same person. The images themselves generally come from a source like Flickr or something where you get a large variety of different images. Right? Normally all you have is the image, so you don't have the camera parameters. Right? Which sometimes good, sometimes bad. Well, generally bad. You can always ignore them. Right? The other version is the 3D version. So given an image, try and infer it in 3 dimensions. Right? These are normally done with motion capture systems. Right? Setting those systems up is quite expensive. Right? Once you have them set up, though, you can capture frames very, very quickly. You can just record at 60 frames per second and record 10 minutes, and you've got a very large number of frames. Those frames don't have very much variety between them, though. All right? And that can be troubling. This image comes from a dataset called Human 3.6 million. Right? There's 3.5 million frames in there, but they're all taken in the same room, and there's only, I think, 10 or 12 different subjects. Right? They're all wearing the same clothes when they do it. They've all got these little motion capture dots all over them. So it's very easy to train a very good network under those situations that just relies on finding those dots. Right? Obviously, that's not very helpful outside of a motion capture environment. And if you already have the motion capture environment, you don't need a network to learn these things. Right, so pros and cons to both approaches. The other thing some people look at, and what I focus on, is this like 2D to 3D lifting module. So if you have a really good 2D human pose inference system, right, and you can take that 2D input and try and infer what it looks like in 3 dimensions, right, we call that a 2D to 3D lifting module. The idea is if we train our network on data sets that have been collected under a very varied environment, then combine it with our lifting module, then we'll have a 3D pose estimation system which is good in the wild. I'm not going to focus so much on the end-to-end problem. I just look at that middle section, which again is a bit of a toy problem. It's not incredible. It does depend on having a good 2D pose inference system out the front. But for the purpose of research, that's what I've decided to focus on here. Right. Okay, so how do we do this? Well, there are lots of methods. The one I'll compare against, right, is this paper back in 2017 by Martinez et al. At the time, a lot of people were doing some fancy stuff with this lifting, and these guys pretty much came out and said, hey guys, if we just take approaches that work really well in other areas of deep learning and just put them all into one network, then we get pretty good results. Right, so they took linear layers, they took batch norm, they took ReLU, they took dropout, right? They took skip connections, and they just like plonked them all into one network, trained it, so 2D pose in, 3D pose out, and they beat most of the state-of-the-art results at the time. Right? Again, that's for this particular data set, right? It doesn't generalize well to different camera poses. In the data set itself, there's only 4 different camera poses, so it does very much overtune to those camera positions and those specific cameras. Right, but they just say, look, this should be our baseline. Right? Question?
Why does camera pose matter, assuming that people didn't have any preferred orientation in the room?
So one thing is like depth, like overall scale is ambiguous. But if you know the camera is always pointing at a certain angle down and you can see their feet, then you get quite good at inferring scale.
So not rotation, but distance and height and so on.
Those sorts of things, yeah. Right, and that's a great baseline. I think that's a fantastic paper. I think if people are overcomplicating things and doing fancy things and they don't get better than that, then they need to sort of reevaluate why they're doing this, right? But that doesn't mean it's perfect. I have a few issues in principle with this approach, if you like. All right, so the question is, do we need millions of parameters for this 2D to 3D lifting thing? Essentially, we're just trying to infer depth, albeit with ambiguities and self-occlusions. Right? And I'm very happy learning a little bit, but do we need millions of parameters? Right? If we just disappear back to this network architecture, this linear to linear mapping, right, in the middle, that's got something like a million parameters. Right? And there's this whole block's repeated twice. So we end up with about 4 million parameters over this whole thing. Right? Do we need 4 million parameters just to infer depth? Right? And you can take the number of parameters down, and under this architecture, you see that the results do actually decrease. Right? So I'd say under this architecture, yes, you kind of do need that many parameters. Right? But in general, can we design the architecture better so that we don't need those 4 million parameters? Right? Next question is, can we use simple computer graphics techniques to reduce how much we need to learn and to encourage consistency? We have really good models of how light works, right? Assuming you're not passing a supermassive black hole, right? Light travels in straight lines, right? And so we would like to use the fact that we know how that works rather than trying to learn it from scratch for each computer vision problem, right? And lastly, can we devise a model which takes advantage of camera parameters if we know them, right? I work in a robotics lab, right? It's fairly easy for me to convince the roboticists that you'll be able to know the camera parameters in advance. Not all circumstances, but a lot of the time you will know those camera parameters. Right? If we train a model and we want to switch cameras, do we have to train that model from scratch? Right? Or can we just switch some camera parameters in our model and have it work? So, we're just going to discuss a few ideas. Oh, question?
Yeah, so for this model with millions of parameters, was that trained on the data set you mentioned with 3.6 million images?
Yes, yeah, so it just dealt with that set.
And if you train it on significantly fewer images, then it will lose accuracy?
Presumably. I never tried that. But yeah. I mean, it never actually used the images themselves. It just used the 2D and 3D coordinates.
Sure.
So you can even like virtually simulate that. If you have 3D in one pose, you can always simulate a new pose. A new camera pose, because you know the camera parameters. But yeah.
You put 2D pose in this data set for the invisible joints. Is there any label?
There are in the data set. The occluded joints are labeled because there's a system of cameras all around. So it doesn't just come from that image. So the 2D joints came from a variety of sources. One was just the ground truth projected, right? So the real true 2D points. The other one was a network that they trained on a different data set. All right. So there it's doing its best to infer the occluded joints, but obviously it's hard if you can't see them. And then a third version sort of took that model and fine-tuned it on this data set. So again, it still has that occlusion issue, right? But it gets very good at detecting little motion capture dots. So let's discuss a few ideas about how we can sort of do this. Right, idea 0, definitely not a paper in this. We'll just discuss it very quickly because it will help the other ideas. The idea is, well, if we know where the points are in 2D, let's just hypothesize, or let's just find a 3D pose which is consistent with that 2D pose. Right, and let's just optimize however we want. Right, I think you can do it with a least squares one step, bam, it's just convex. Right, the idea is we just start anywhere and we move our 3D pose until it lines up exactly with our 2D pose. All right, so over on the left, we actually have both the ground truth and the our solution, right, in 2D from the camera's perspective. All right, but if we look at it from a different angle, over on the right, we see that they're really not the same pose. Right? This is never really going to work. It just says take a bunch of points and move them until they line up with a ray emanating from the camera. Right? We're not taking into account feasibility, what human joints can do, limb length consistencies, angles, all these other things. Right? And a slightly more complicated version might try and hard code all of those constraints, give yourself a skeleton model, know how long the limbs are, know that elbows can't bend backwards, and these sorts of things. But that gets fairly tricky to enumerate all possible things, and you'd find that even once you've done that, you'll probably have some possible poses which just don't look good. Right? It's very difficult to define that idea. What makes a pose feasible? Right? And that's where I think we should start learning things. In this current model, there's no learning. Right? If you have the 2D pose, you just plug it in and you'll get a 3D pose. Right? But that projection stuff is all very, very well understood, very simple. We're not doing any crazy projection. We're just dividing by the depth with some camera parameters in there. Right? So idea one just says, well, theoretically, let's try and search only the feasible poses. For the moment, I'm going to ignore how we get that definition of feasible poses. But let's pretend we have all possible 3D poses in that sort of slightly darker area. All right. A subset of that, a manifold inside that, we're going to define as feasible poses. So points on that blue line are feasible. All right. Then for a given image or a given set of 2D observations, we'll end up with another set of points or another set of poses which are consistent with our observation. Right? They're the ones that line up. Right? And obviously not every one of those consistent poses will be feasible, just like not every feasible pose will be consistent with a given observation. Right? But hopefully there'll be some intersection given by those little orange dots, and we'll try and find those orange dots. Now, there's still going to be a few. There are still going to be ambiguities. From a single image, we can't do away with those entirely. Right? But for the moment, we're just going to say let's hope that getting to one of those orange dots is good enough. Right? It's a feasible pose. It agrees entirely with our observation. It's about as good as we can do with a single image. Right? If we get a different observation, right, that'll correspond to a different set of consistent poses. Hence, the intersection will be different. Right? So the idea is we train up, or we learn this feasible set of poses once, right? And then for each different observation, we look for a different intersection. Right? At inference time, we start with some hypothesis, like this black dot, right? And then we just roll our ball down the hill, right? Or roll our ball towards the red line. Right? And we do that with any optimization scheme we want, right? If it turns out that we can make it convex, then we use some convex optimizer. As it is, we just use normal gradient descent methods. Right? Different initial position will get us to the different point. Right? This can be handy if you run some sort of like particle filter. You can get an idea of all possible consistent and feasible points. Right? If you plonk down 1,000 points, you'll get a bunch at one point, a bunch at the other. Right? That can sort of represent some measure of uncertainty, or at least the distribution of the intersection of feasible and consistent poses. So I left that big question at the beginning, how do we define that feasible set? Well, we trained a generative adversarial network, a GAN. Anyone not know what a GAN is? No, there's lots and lots and lots and lots of literature on GANs. Every conference you go to, there's 17 new GAN architectures. We used a really simple Wasserstein GAN, nothing too crazy. For training, we used just normalized 3D poses. So we rotated all the 3D poses so the hips were pointing forwards, they were all the same height. And the vertical, the z-axis was the vertical axis. Right, so we trained, and the idea is that once you've trained that GAN, if you've trained it well, the generator will always generate feasible poses, so long as your input's not too far away from the normal distribution under which you train. We also have a discriminator. at the end of that, which measures or gives some measure of how feasible a given pose is. We experimented with augmenting our loss with that discriminator loss as well, and we found it didn't really need to be there. After we trained that up, we used just standard gradient descent-based optimizers to minimize consistently loss. I think we used LVFGS, but just off the shelf, didn't do any tweaking, just plugged it in. All right, it's a quick video here, which I didn't quite work out how to do nicely, but boom, look at that, integration. It actually worked. I wasn't really expecting that. So after training our GAN, right, we've got a bunch of knobs. They're like our GAN input. As we move those around, we'll get a different generated pose. And the idea is that pose in 3D should look fairly feasible. It's a weird skeleton. It looks like it's got a very high belly button or something, but that's just how I chose to visualize these. Right? There's no sort of center hip joint. All right. Seating was hard. GANs have this thing called sort of mode collapse, and you can get to seated poses, but they're not amazing. At runtime, right, maybe let's pause it there for a second. We have some initial observation. So that's this guy up here. And we just started with like a random GAN input. So we have some pose which has nothing to do with the image, right? And then we tweak those knobs that we had in the previous section until we match up with what we see. Over on the right, you see a different angle in 3D. Right, and you just go until you sort of align. And in this case, we took enough iterations until it just said it was converged, but we didn't really worry about optimizing that too much.
How many parameters do you have?
So in this one, pushing the limits of my memory, but I think we had 16 inputs for our best model, so 16 GAN, and then like 100 hidden layers, and then number of joints out times 3.
You optimize over just 16 variables?
Yes, you optimize over 16 variables, plus a rotation about the z-axis, plus a global offset, plus a scale parameter, I think. Yes.
Since your goal is simplicity, how does this compare to a parametric model for the density that you're training your GAN to model?
Like a hard-coded...
or anything else, because you're using the GAN to approximate some unknown distribution, so how much better is it to learn that than to actually use a known model?
Didn't actually compare. I would suggest probably not amazingly better, because we know lots about humans, and there's lots of work that's been going into those handcrafted models. I guess the idea here is, let's see if we wanted to transfer this to a different domain and all we had was a data set, then that's all we need. Is that?
Yeah.
Yep.
And to learn that Latin representation, you use GAN, but why not VEs, for example?
GANs were the craze. It was my first year of my PhD, and they sounded pretty cool. I mean, it fitted exactly what I wanted. It's something that generates only feasible things. From my understanding, VAEs tend to sort of smush things together. They sort of get averages of things, whereas GANs are better at producing sort of distinctly separate.
But you also get like a distribution with the VAEs.
Yes, no, I mean, I'm not saying this is the only way of doing it. I like the idea of VAEs a lot. But GANs are cool. I had to jump on that bandwagon before I realized that everyone's jumping on it and no one pays any attention to them in conferences. No, GANs are good, but I'm a bit bored of seeing them at conferences. Question?
Do you form in local minimas? Do you have to do multiple starts sometimes?
Sorry?
Do you form into local minimas? This optimization?
We didn't observe much falling into local minimas. We did see sort of mode collapse, which you'll see in a second, for things which are less common in the... oh, wait, we've already skipped it. My bad. Where do we do the seating one? No, still ahead of the seating. No, sorry. He sits down at some point. He'll come up soon. So for seating stuff, there's a few in the data set, but there's much more standing up, walking around. So again, just decided that was hard and decided not to try and play very nicely. We did just go for sort of simplicity over anything else. We just wanted to say, take an optimizer off the shelf, plug it in, see what happens. I'm not trying to suggest this is as an exhaustive study of all the possible things you can do with this sort of idea.
And this just seems to be a bit of an offset in this, maybe in the Z direction.
Yeah, so that's mostly the depth. So and again, if it's turning right to the side, then sometimes he flicks around backwards and forwards because there's just a high degree of variability there. Again, if you took higher level 2D features, you could probably sort of learn which way they're facing, but when you extract just the points, you lose that orientation information when they're exactly side on. Here's the mode collapse. This is terrible, right? Sitting down there doesn't happen very much in the training set, so we see we're really struggling over on the right there to work it out. But not here. So here we just do them. I think I might have used like initialization thing, but the optimizer jumps around a fair bit. So there's no temporal smoothing. Here we have some temporal smoothing, right, where we just sort of apply an additional loss, which says things can't move very much between frames, right? And you see if you weight that too heavily, he tends to run in a circle that's just a smaller radius, which is a bit unsatisfying. If you do it just a moderate amount, then you get a sort of smoothed out version. Still not very satisfying. He tends to glide over the ground, right?
Is that temporal smoothing on the latent variables or on the...
No, on the output. So that could work as well, right? I didn't really love this idea, right? It was a sort of first stab. We came up and all those things are correct. I don't love the fact that you're hard coding how much smoothing there should be, right? We did play around with trying to generate sequences, and that got hard. Training a GAN to generate a feasible pose, we never sort of saw anything pop out that really looked feasible. They just sort of moved from different feasible poses to other feasible poses, but not as a feasible sequence. But the thing that really kept me awake at night, right, the thing that absolutely terrified me, was what happens if our blue thing looks like this, right? That could be a perfectly generated output space, right? And that every single pose that's feasible could be in that blue thing, and every one of those blue points could be feasible. Right? But when you try and use this in your optimization thing, unless you're very lucky, you're going to fail. Right? If you start off on either of those positions, right, you're never going to get to a consistent pose. Right? And now we didn't really see a huge amount of evidence of this, but it still terrified me. Right? And I wanted to move away from GANs, so we decided idea number 2. Right? So idea number 2 was, let's try and learn a loss function. Right? Obviously, we can't have the reconstruction loss. We can't just minimize the reconstruction loss. We can't move our 3D points towards the real 3D points at inference time because we don't have the real 3D points. Right? But if we had a function that approximated that reconstruction loss, right, then we could just minimize that function. Right? And if that function is sufficiently close to the original function, right, then we'll be all good. Right? So that idea would be here's our loss function with our desired point. Right? Here's where we want to get to. Here's our original loss function, or our true loss function, which cheats, which uses information we don't have. Right? And there's maybe our learned loss function. Right? Well, let's just take those two and let's look at the difference at a bunch of points, and let's try and pull those guys together. Okay. So this blue curve would be a parameterized loss function, right, which can know the 2D joints, but it won't know the 3D joints. Right. As it turns out, that's a problem that's a little bit harder than we need. Right? It's overly constraining. At the end of the day, we don't want a function which is exactly the same as the true loss function. Right? What we want is a function which behaves similarly to the true loss function under optimization. Right? So if we have that function and that global minima, we look at where our ball rolls. Right? We end up over there. Right? We want it to be over here. So let's look at the difference between where we end up versus where we want it to get to. And then we also add in a bunch of other ones to encourage us to get there fast. Right? And then let's tweak our loss function so that next time we run it with this input, we'll get closer, or the optimization process will get us closer to where we want to be. Right? So that's the difference between learning a loss function and learning a loss function fit for purpose. Right? So long as our minima are co-located and our surface is such that under gradient descent or whatever optimizer we use, we end up in the same place, right? Then we're happy. doesn't matter if we're off by an offset or, it's slightly different gradients here and there. Question, start.
So how do you enforce that you don't have different local maxima? You said, or minima, you said essentially the learned loss function should have a similar loss surface so that SGD actually ends up in the same place.
Yes.
But how do you enforce that?
We don't enforce it so much, but we penalize ones that don't.
How do you recognize that they don't do that? Without sampling essentially exhaustively what the surface looks like?
We just do gradient descent. We literally sort of do gradient descent.
So what you're enforcing is that for one example, it behaves the same way?
Yes, but then we'll take we do that. That's one example in our training, and we iterate over and over.
That looks like an energy-based model, is that?
That's exactly what we're getting to, right? And yes, that specifically is not my work, but the choice of energy functions is what we'll discuss. So just to summarize the ideas, idea 0 was let's just try and minimize the reprojection loss. Oh, sorry, question?
So I'm not quite sure what the loss function is. Is it a loss function to penalize infeasible poses?
It's some loss function. I'll get to the specifics.
Okay.
But yeah, it's something that combines feasibility with consistency. Right? Or really, it's just a function that we hope has co-located minima with the true loss function. Not even that, one that behaves similarly under optimization. So if you have momentum and there's a few things that momentum can get past, we don't really care. Just to summarize, I don't love this slide, but I figured I should have one slide with maths in it. Option 0 says let's just minimize the reprojection loss. Doesn't really work, doesn't take into account any sort of feasibility. Idea 1 said, well, let's only optimize the feasible poses. Right?
So P3 is the set of 3D joints, essentially.
Yes. They're ordered, so this, yep.
Yeah.
So a tilde means an inferred something. P3 is the 3-dimensional one, P2 is the 2-dimensional one. And a star is an optimal, I suppose, or like the output. So idea 1 said, let's train our GAN in the first stage, and then in a completely separate stage, let's just optimize that surface. Right? Problem being that surface hasn't been optimized for optimization. It's been optimized for feasibility, right? So it might be a hideous surface to optimize. Idea 2 says, let's do them at the same time, right? Let's define our P3 as some minimum over the possible poses, right? Where our energy function, which I'm calling E, right, is just trained such that works well. I think the pictures do a better job than that slide, but if you want to write that formally, you can.
So the actual loss function in idea 2 is still an L2 or an L1 or something?
I think
comparison between the 2D and the projected 2D
yeah,
points.
the loss function is the reconstruction loss, so the L2 loss of the 3-dimensional poses.
So those norm bars are L2.
Oh, sorry, yeah, there
Yes,
probably should be some squares in there.
Yeah.
So the
Sorry.
norm bars are L2, so the actual loss of your optimization problem is still convex. So what you're learning, I'm struggling why you call what you're learning a loss function, because the loss function is the L2 difference.
Okay, sure. Energy function.
Okay.
If I call it an energy, is that?
Yeah.
It's kind of trying to learn something similar to the loss function.
Thank you.
Okay.
Sorry, in the last line there, P3 without a tilde means what?
The true, the label.
So ground truth?
Yes.
Okay.
Cool. So there's a picture that kind of summarizes the idea. This is specifically unrolled optimization. So I said earlier you can construct your energy function to be convex and then solve the optimization in one step or something. We chose to go with unrolled optimization. So this F here represents, that was definitely wrong. Sorry, where were we? There we are. This F just represents a step of gradient descent, right? You can throw in momentum if you want. If you really want to code up an atom version, you could do that. It's just some iterative update step, which is itself differentiable, right? We optimize our energy with respect to the input, or the 3D input Y, which also knows about the 2D input X. This is like our 2D pose. This is our 3D pose. plug them both into this big red box, this energy function, right? We get some scalar output. We use some gradient descent based on this to optimize our y with respect to that loss function, right? And we end up with a whole bunch or a sequence of inferred poses. Right? And then we take each one of those, we compare it to our label, we'll get a loss, right? And we use that to tweak the parameters of our energy, and we can also tweak the parameters of our optimizer. Right? Things like learning rate or momentum of the inner optimizer can be optimized. So we're not just optimizing the surface, we're optimizing the surface in conjunction with the optimizer. Right? And that hopefully will get rid of these hideous surfaces, right? Because we're learning surfaces that are good to optimize. As I said, this has been done before, right? This David, I believe, is Belanger, has done a few of them. He wasn't sort of the first, but he sort of formalized it. He did some stuff with convex stuff. He did some stuff with unrolled optimization, and there's some really good papers. There's that one and a subsequent one, which I would encourage you to look up if you're interested. All right, here's the one slide of code, which is a bit scary, but just it sounds a bit scary, but in terms of code, it's not too bad. All right, the idea is we set up some initial inner learning rate. We extract some visual features, right? And if your labels are 2D poses, that can just be the 2D poses. It can just be the identity function, right? We have some initial estimation network, right? Which could just be random. Doesn't really matter. Well, I mean, it might affect results, but it could be very simple, all right? And then we also compute the outer loss just to get us started, right? And that will encourage us to get that sort of trains the initial estimate network a little bit, if it exists, right? And then our inner optimization loop, we don't try and solve to convergence, right? The theory says you can do it to convergence. We just do it for a fixed number of steps, and that number of steps doesn't have to be large. For the human pose stuff, we had, I think, up to 16. For the reconstruction stuff, we had bigger networks, so I think we did 4 steps, right? So even less than having co-located minima, we just want a surface that will tend to roll balls downhill towards the true global minima, or a minima. Right. Our update step was very simple. Here we just had gradient descent, like just vanilla gradient descent. We also experimented with momentum. As it turns out, I didn't really see a huge difference between the two. Right. If you train it with momentum, the surface just ends up being slightly different. At the end of the day, we just plug that into a standard optimizer. Right. I think, what did I say? Outer optimizer. Didn't specify an optimizer. I think we used Atom. And we just optimize with respect to the learned parameters. Right? And they're not just the parameters of the networks, they're also the parameters of the optimizer. Right? As I said at the very beginning, you do want to make sure this inner loss network is differentiable with respect to network parameters, and that derivative is differentiable with respect to the network parameters. I'm not convinced ReLUs definitely won't work. I'm happy to be convinced that ReLUs won't work, but in practice, they didn't work very well at all. So we just used soft ReLUs. Like, nothing too crazy, soft ReLUs worked pretty well. All right. So the rest of the talk is pretty much what those red boxes were. As I said, this framework's been set up before. I'm going to start speeding up a little bit because we're running a little bit short on time. All right. But for human pose stuff, we just said, well, let's take our 3D pose here. Right, let's put them inside the red box. We're going to project them down to 2D. So we have what we would see under our hypothesis. We have what we actually see. We plug that into some energy, and that's supposed to represent the consistency. Right, at the same time, we plug our 3-dimensional pose into a separate network, right, which is supposed to represent our feasibility. Right, or you could think of that as learning a prior over 3-dimensional poses. Right, and we take the output. We optimize with respect to our y. And hopefully if we do that, we'll end up with a pose which is both feasible and consistent. We could have just used a reprojection loss for this energy up here, something that compared the two. As it turns out, a lot of the 2D data sets have different joint annotations to the 3D data sets, just subtly. They have like a different number of joints, 17 joints in the face sometimes. So instead of that, to make it a bit more generic, we just said, let's take our two versions, our inferred 2D pose and our observed 2D pose. All right, let's concatenate them together and then take the paired difference, the paired distance between those joints. So pairwise distance between those joints. That has a number of nice properties. It's rotationally invariant, all these other things. More important for the 3D pose, you have rotational invariance and some nice things that just come along, which are generally good. Or mean you have to learn less things. These networks, I call them deep networks, but they're not really deep. They're one hidden layer followed by one output layer. So very, very small. You've got roughly 100 inputs, hidden layer of, I think, 64, and then maybe 8 outputs, which we sum together. So all up, very, very few network parameters. In terms of performance, it's a little hard to see, but the solid lines are the ground truth or observations, right? And the dotted lines are the inferences after a number of steps. So we see if we're in the camera view, we start off fairly decent, but there's still a bit of a discrepancy. After even one iteration, we've synced up very, very nicely, right? And on other views, right, we don't go terribly away from feasible poses, right? It does generally do fairly well. All right, I do need to speed up just a little bit. Quantitatively, here we see our baseline methods in the red and blue. So that's whether you have one block or two block, and then each dot represents a different number of hidden layers. So in general, you've got more computation, more learned parameters as you go to the right. On our red and blue dots, the size of the dot is the number of parameters in that model. Right, down the bottom we have the number of operations, and vertically we have the error. So down is good, left is good. The black dots were all exactly the same set of models. The only difference was the number of iteration steps we took in that optimizer. A number of iterations rather. Right, so with 0 iterations, it's just exactly the same as the baseline methods. Right, even 1 iteration gets us a long way towards better. Takes more, a few more steps, but decreases the accuracy a fair bit. Right, I think we had 0, 1, 2, 4, 6, 8, 12. It gets better. It does eventually plateau. It doesn't really get much better than that last number. In terms of accuracy, we were just like a millimeter or two on average worse for most. I think this is our most favorable plot, so we put it in the paper. But on average, we're typically, a millimeter or two on average worse. In 3D over the course of meters, I was okay with that. But we'll just say, just because there's less multiply adds doesn't necessarily mean it's faster. At least on GPUs, these big models tend to just use up more cores. These tiny models just don't use up all the cores, so they don't actually take full advantage of that. If you're on a small embedded system or something without that, 2,000 cores, I think you would see a very decent speed improvement.
Do you use some number of iterations during training? And
each one of these was trained separately. Theoretically, you could adjust that at evaluation time. We didn't really investigate that. Does that answer your question? Yeah. So you are sort of fine-tuning the surface to the optimizer and vice versa. And yeah, we just said, let's take a fixed number. All right, I don't have very much time, but I'm going to try and get through this maybe a little bit faster. 3D reconstruction is sort of still 3D inference from monocular vision, but the idea is given an image, let's try and get some sort of 3D CAD model representation. We decided to use voxels for this work. A voxel is just a 3D pixel, if you're confused by that or haven't heard that terminology. Before we do that, let's do a really quick aside into deconvolutions in general. Deconvolutional networks are often used for semantic segmentation stuff, and they pretty much take an encoder, right, down to some latent variable space, and then a decoder, which almost always just like turns this around in terms of the number of filters, size of things. As it turns out, if you do that, the number of operations doubles per resolution, and the number of operations stays the same, and I think the memory requirement doubles for images. In 3D, the number of operations per resolution doubles, and the memory requirement quadruples. What that means is you generally end up with models that do something like this, right, which take maybe a 128 squared image and output a 3D CAD voxel grid in like 32 cubed resolution, which is just a little bit dissatisfying for me. So given that you had work that radically reduced the number of parameters, right, and number of operations, we decided rather than trying to reduce that number, let's keep roughly the same number and try and increase the resolution for our 3D inference. Right? So everyone's, I'm sure, is pretty comfortable with the idea of coordinate transformations. Right? That's not too hard. We need some concept of projection. Right? And the first step to that is normally doing some coordinate transformation. For this work, rather than taking our output in camera coordinates and transforming it back to world coordinates and comparing it against some world coordinate reference thing, which most people do, we transformed our labeled dataset to frustum or clip space coordinates. Turns out it's a little bit faster. But we still have this question, like, how do we project probabilistic occupancy grids? And that's a rather... you can come up with lots of ways in your head that might be great. The most obvious one might be what I call sort of max projection. All right, so if we take our 3D voxel grid reduced to 2D for visualization purposes in clip space, right, so in frustum space, so max projection just says, well, let's go along the ray. Right, let's just take the maximum value of the probabilistic voxel grid along the ray. If we take that and we compare it to some image features that we got out of our image, for illustrative purposes, I'm just saying, let's pretend we've got a silhouette. So some pixels are black, some pixels are white. Right? Then we can plug these guys into one CNN, right, and get some learned energy function. Right? So in this case, you'll see like there was nothing here, but there were lots of guys along here. So really, we want to be able to space carve that out in like one shot. We want to say we saw absolutely nothing. We saw background. All of these guys should be off. Right? Problem with going through this, if we've got this max projection, right, when you do that update step in the inner loop, you end up with very sparse gradients. So you'll still get an update, right? Those guys will get changed slightly. The green ones will go up a little bit and the red ones will go down. But you won't touch the rest of them. You'll only ever touch one. And you can try and do some sort of softened version of a maximum, right? But you don't really solve the problem there. You just smear it out, right? So we played with a different idea, right? We said, let's just use concatenation. You can not call this projection if you want. If you just want to call this concatenation and not concatenation projection, feel free. But the idea is we just take all our voxel values and we sort of concatenate them into an image feature. So we take a 128 cubed voxel grid and we convert it into a 128 squared image with 128 features. All right, we take that, we concatenate that with our image features, plug into a CNN, and then we can update all of our values. All right. It's not quite as straightforward as the 2D image version, like you, the 2D pose stuff, right? Again, because projecting these guys is a bit tricky, right? But we found this worked quite well in practice. So now we're not going to try and split it up into an explicit projection function, reconstruction loss and prior loss, right? We just have these CNNs, which say how consistent is this pixel feature with this array of voxel values. All right. We still want to take advantage of some of the hierarchical features or characteristics of sort of UNet style architectures or convolutional architectures. So we just took a couple of different image networks. Here we see ModelNet version 2, no, MobileNet version 2. But we also experimented with the bigger Inception v4 ResNet. As we have our beautifully illustrated probabilistic voxel model over on the right. All right, we just take each one of those, or take that multiple times, and we're just going to pool it anisotropically. All right, so up the top here, in our image, we've got high resolution, low number of features. All right, we're going to combine that with something that's been pooled, such that we have lots of fine-grained resolution in the image space, and not that many features, so not many voxels along the depth. And we just do average pooling there. Right, we do that for a bunch of different resolutions. So there's a one-to-one mapping here. Right, so the architecture ends up looking something like this. Right, we only extract the image features once, so we pass it through MobileNet and then do a UNet style upsampling as well. Right, we take those features. Right, we take our voxel grid, we pool this in at different rates. Right, interpret it as an image just by reshaping. Right. Concatenate with the image features and get a loss function out. Right, again, go through and we optimize this Y tilde. I'm going to skip over these results because we're really running out of time. In short, the we found at 32 cubed resolution at least, the changing of the data set from world coordinates to frustum coordinates didn't make the problem any easier, made it slightly harder in fact. We propose that's because for things like planes, right, you can pretty much plonk down the average of the data set for plane and you'll get roughly right. They've all got 2 wings, they've all got a fuselage. As soon as you throw in different camera rotations, it's harder to learn those priors. And not only that, our models did slightly better than just like a baseline. That's being said, we didn't really target the 32 cubed resolution, but we wanted to compare against the baseline and they don't work at higher resolutions. Right? At higher resolutions compared to other people, we did slightly better in some categories, slightly worse in others. Cars, we did slightly worse because they're kind of like blobs. So this Matryoshka Russian doll network sort of layered things on kind of like a Russian doll, and so they're quite good at cars and blobby things. Whereas things like tables, we did significantly better, right? Because we were able to take advantage of the sort of space carving aspect and really leverage those computer graphics techniques. In terms of results, really running out of time here, but in short, depending on what you do with your loss function, you can either make a conservative loss function, which does better on those metrics. Right? If you make your loss function look more like an intersection over union, then your intersection over union results get better. Over on the right, they actually look worse, I feel, right? But they actually score slightly better on the metrics that we chose to target. Right? Those metrics don't have a feasibility component, they're just intersection over union. You do get a bit of depth shadowing. This example here highlights the depth shadowing. So if you look at the same perspective as the camera, right, you get no false positives, so it space carves pretty much perfectly, right? But if you look at a slightly different angle, it doesn't really know where along those rays it is, so you get this very slight depth shadowing. But it's not massive, I hope you agree. Right, so it has learned to pry out over those shapes quite well. I think I'll skip. Okay, so just a really quick summary. Our networks, essentially, they're generic decoders that are parameterized mostly by an energy network. So we don't really need to write this explicit decoder, right? So we don't need to write a deconvolution. Nowhere in our reconstruction thing did we have a 3D deconvolution network, right? We just had a convolution network, and even that, we did some pooling hacks to make it not too computationally intensive, right? They incorporate explicit computer graphics techniques rather than learning them, right? If you really want to, you could just say they're just specific customizable recurrent layers, right? I think that's takes away, but if you want to do some theoretical analysis, you can take all the stuff from RNNs and sort of apply the generic RNN idea here. We're going to skip that. Any questions?
Thank you. It seems to me, at least on the first viewing, that your energy networks are some kind of regularizer, right? You enforce penalties on the gradient field of this encoding that you're learning in the middle. So my question would be, is it possible that those things, as in why should I use those things over, for example, spectral normalization to bound the Lipschitz constant, or, enforcing some properties of the Hessian or the SVD, because your networks are so small that you could use those techniques, right? You can compute the stable rank of a single layer network. You don't need to do gradient steps to ensure that mapping is smooth necessarily.
You don't need to enforce it. I don't think I agree with your assertion that it's just a regularization. Why? I'm not saying you're wrong. I just don't. I don't understand your assertion. That
it just seemed to me, maybe I'm wrong because I'm not familiar with this particular bit of the literature, but it seems to me that if you're doing gradient descent steps inside this, and you're enforcing some properties on the mapping, right, it should be smooth, for example, in the local vicinity of where you are currently in this energy function. So to me, it seems that this is a regularizer on the curvature of this mapping, and so you could think of it in terms of touching the Lipschitz constant or the Hessian at that specific point. And there's been all this work in GANs with spectral norm, stable rank norm, and so on. That seems very familiar, but just a different way of doing it. So I'm guessing the question is more like, have you looked at any of these things, or do you see this as a valid point?
First question's easy. No, I have not looked at these things, and I am not familiar with that literature. So would defer. Sounds like you are. So if there's a connection there, fantastic. Yeah, sorry.
Thanks. No, just curious.
I would say that those things try to regularize the curvature and don't. And you may have observed, I like your observation that this is somehow regularizing the curvature, but it may be a different or more effective way to do it with sampling rather than
Exactly.
quadratic approximation.
This is why I think it's so interesting, because it's also quite cheap just to do a couple of cents rather than computing, say, like trying to compute the Hessian or something, which is really complicated.
So, I mean, essentially, you just want a function that behaves well. You're not trying to enforce that. I mean, in the network itself, I did try with ReLUs and it didn't work very well, and I'm willing to be convinced that that was never going to work. I've read people that say it definitely never will work, but they don't really justify it. I feel that the derivatives with respect to different things, so it should just be like an on-off thing. Anyway,
Thank you.
Again, yeah.
I have a question. In the first bit of your talk, the illustrations reminded me a lot of manifold learning techniques. So I was wondering if you compared to any of them. And on the second bit, when you were trying to learn the function, the fact that you were limited to smooth, sigma sub-ReLUs instead of ReLUs, do you think there's any link of? Because on the first bit, when you show the nice manifolds, and you put a gun there with ReLUs, you can claim maybe you don't get something smooth and you have jumps.
Yep, I can't remember exactly what my generator architecture was like. I think there was soft ReLUs in one and hard ReLUs in the other.
Was also.
Yep. So I mean, they were purely illustrative, me dragging and dropping things. That they weren't anything to do with what actually came out of the GAN. Does that answer your question?
Yeah, I think the first question was have you looked at any more classic manifold learning techniques and see how to doing optimization over the manifold would compare to what you were doing?
No.
Do you mean like GPLVM or something? What's a classical?
Yeah, something like that. Something where the Latin variable, you're forcing things to be smooth and to be connected through your learning on your learning data set.
More questions? Toby?
With the volumetric work, did you look at all at, rather than an occupancy grid, which is quite coarse, did you experiment with other representations, like, for example, the truncated sine distance function?
Oh, I'm glad you asked. This whole work started looking at sine distance functions, and I wanted to evaluate sine distance functions to point clouds. So I needed to sort of do the isosurface extraction there, and I did that by rolling balls down hills in the learned sine distance function. And then I had an optimization step as part of my evaluation, and it sort of went from there, and we didn't have too much success there. In terms of future work, I want to start applying this to point clouds, and as soon as you're starting to move points around to a global minima in a point cloud, that's getting very close to isosurface extraction. Problem is you need a continuous function with respect to the inputs, and you would like some sort of hierarchical thing. PointNet isn't hierarchical if you know anything about PointNet. PointNet++ isn't continuous. Anything that uses a fixed ball search isn't continuous. I guess I haven't tried. Maybe it just works well even though you've got discontinuities, but I feel that optimizing a discontinuous function with gradient descent is not going to be pretty.
Yep.
So yeah, a lot of work I've been doing recently is more on just general point cloud convolutions. How can we make those things efficient so that you can be doing it inside an inner loop, and also continuous so that it makes sense. I would love at some point to get back to the sine distance functions because I think they're really elegant, so long as you don't have to evaluate them on a grid.
Okay, thanks.
Why do you think evolutionary methods might be good for this thing on the right?
Don't know, haven't tried them though.
Cool.
I'd like to go explore.
Cool. Yeah.
Yep.
About how you initialize your optimization at runtime.
So we normally had a small deconvolutional thing. So in the human pose stuff, we just use exactly the same model architecture as the baseline, just with 10 times fewer hidden layers, hidden units, and only one repeated block, so it was just much, much smaller. For the 3D stuff, we just used a 3D deconv thing that went up to 32 cube resolution, and then average pulled out, I think. Just did some dirty hack to make it big.
But could you take, like, for each front end the state of the art, none?
Yes. So you can think about this as a refinement model if you want. Each step is just a small refinement. Yeah. We didn't really. I mean, we took basic input, like for 3D stuff. We took a fairly simplistic approach, but that's because the focus was on the refinement.
Noting that clock is 3 minutes slow.
Okay.
I think we'll wrap up here. Thank you all. Thank you very much.
Thank you very much.